Basically, we talk about how to give neutrinos a mass. And the first way to do it is called Dirac mass terms. And this is the simplest way to do it. And the way to do this is to introduce a right-handed component for the three neutrinos, nu e, nu mu, and nu tau. And so this will be the SU2 singlet. And it's very similar to, actually identical to mass term. How the charged electrons gain a mass. So I will not discuss any further about this. And then the second one is called von Jorana neutrino, von Jorana mass. And here we have to introduce a charge conjugation matrix. Or C, and the C turns out to be I, 2, 0, and the representation we are using is 0 equal to 1, 0, 0, minus 1. And the space components of gamma matrices is 0, Pauli matrices, 0, and the gamma phi is equal to 0, 1, minus 1, 0. Okay? And the charge conjugation C has the property that C gamma mu C inverse equal to minus gamma mu transpose. And the C is anti-symmetric. And also C gamma phi C inverse equal to minus gamma phi transpose. Then the charge conjugated field is defined to be C psi bar transpose. And we can also write this as I gamma 2 psi. And then psi bar C is equal to psi transpose times C. And the psi C, if I just tell you this, it's a little bit ambiguous because you don't know whether I take the left-handed first or take the charge conjugated first. So this is defined to be psi left-handed and take the charge conjugation. And then if you go through all of this charge conjugation and so on, you'll find that this is equal to psi C and the right hand. And so the important point is that psi L, the charge conjugation of psi L is a right-handed field. And so this is very important to remember. And the same thing. Psi R, C, psi, C, left-handed. Okay. Now, this charge conjugation conjugate field, the reason we call it because of the following problem. You start with the Dirac equation coupled to electromagnetic field, like this. Then the psi of C, charge conjugate field, I mu, and here the charge changes sign, but the mass stays the same. Psi C equals 0. So psi is for particle, and psi C is the antiparticle. It has the same mass but the opposite charge. Okay? Okay. Then with all these preliminaries, we introduce the Majorana mass term for L. Okay? And that's equal to minus 1 half sum over L prime. This will be the L and L prime are Flavor indices. Okay? And that's equal to mu L prime, right, left-handed, and then there's a mass parameter and here L prime L, and then mu L. And then you remember that this is a right-handed field, so this is left-handed and the right-handed. That gives you a mass term. And then some Hermitian conjugate. Now I can write this in a more compact notation for nu bar L, M, mu L, C. And this column vector, nu L, will be equal to mu E, mu tau. Last time I showed you that because of the properties of charge conjugation and so forth, this matrix is symmetric, transpose. So it's a symmetric matrix. Symmetric. Then you can look at the Bernanke's book, appendix. It shows you how to diagonalize such a matrix, and this M is equal to a U M U transpose. Okay? And the U is a unitary matrix. And the M is diagonal. IK will be MI, then IK. And MI is bigger than 0. Okay? And then I can put this in here. And M equal to minus 1 half mu bar L. And then I have mu M U transpose. And then I have mu L C. And then plus Hermitian conjugate. And I showed you last time that you can write this as follows. That we have mu bar M, and then little m here, and mu M. And this mu M is equal to mu dagger mu L plus mu dagger mu L C. to show you that from here, look at this. And you see that you might take the charge conjugation of this, the two terms just interchange. So this equals mu n of c. So it's a Majorana neutrino. Neutrinos and its antiparticle are the same. Okay. That's what we stopped last week. So I can now continue to discuss the last way to give neutrino mass, like Dirac mass, neutrino mass, Majorana mass. Then we can put the two together. Instead of talking about the most general case, I'll talk about a simplest case. So this will be Dirac mass plus Majorana mass. Okay? And then I will just simplest case. You have left-handed neutrino and then a right-handed neutrino. And I'll write it down. The master LP plus M equal minus 1/2 left-handed Majorana mass term L mu L C. That's just like this. And then I have Dirac mass terms. And then the right-handed Majorana mass term. Mu R, and then I have mu R C. And then was mission conjugate. Now you can combine all of this in a compact notation. N L bar, N plus B, and then N L C plus mission conjugate. And this N L is a column vector equal to mu L and then mu C. And then you remember that this is a left-handed field, so all these components are left-handed field here. Okay? And then the mass matrix D, what do I go? Yeah, D. Yeah, M plus B or D plus M. We'll have the following form. There's M L from there, and then I have M D, M B, M L, M R. I did not show you how you get from here to there, but you can work it out using this form, and then the connection between the charge conjugation field and the original field from here. You can actually show this very simple, okay? Okay. Now the matrix can also be is symmetric, you can see. It can also be diagonalized. So this M plus E will be equal to O. It's a symmetric, so it can be all diagonalized by a orthogonal matrix. M or P. Okay? And then this all orthogonal matrix is very simple. Cosine theta, sine theta, minus sine theta, cosine theta, the one you are familiar with. Oh, and then the eigenvalues, let me give it a prime, because I'm going to use m for the final answer. So m prime 1 and 2, the eigenvalues, it's very simple, just work it out. It's equal to 1/2 m L plus mr plus minus plus 1/2 square root m L minus mr squared plus 4 mg squared. Okay? Now, because of this minus sign, sometimes the eigenvalue can be negative. So in that case, we will do the following: that the m prime I will be equal to mi, and then multiplied by sine eta I. So this mi will be equal to absolute value of mi, and the eta I could be a plus or minus 1. Now, how about the angle theta? It's also very straightforward, just work it out using the eigenvalue equations. And the sine 2 theta, it turns out that for the double angle, sine 2 theta, cosine 2 theta will be easier to find. So this equal to 2 md, and then the square root m L minus mr squared plus 4 md squared. And then the cosine 2 theta equal to m r minus m L square root m L minus mr squared plus 4 md squared. Okay? Okay, so I want to make use of this positive eigenvalues. So I can write m plus e equal to O, and then I have m eta, and then O transpose, right? And then I can write this as a u m and a u t, and the u is equal to O times square root of a, and it's unitary. Okay? Then we just practice in that equation. Then you'll find that the L E plus M equal to minus 1/2 mu bar M, and then the diagonal mass, diagonal mass matrix, and then mu M and this equal to, I think it's C. And then equal to minus 1/2 mu bar minus 1/2 I mi nu I bar. Oh, sorry. And then I use mu m is equal to u diagonal n L. I already defined what angle is there, right? And then plus u diagonal n L C. It's very much like what we did for the Majorana mass terms there, okay? And this is equal to mu 1 and mu 2. Okay. And if you look at this expression again, you will see that this is equal to mu m charge conjugate. So this is Majorana neutrino. And this is one of the conclusions which bothered me quite a bit when I was learning this subject. It means that as long as you have Majorana mass term in the Hamiltonian, in a Lagrangian, the neutrino eigenstates are always a Majorana. And you may ask what happened if I turn the Majorana mass term to 0. Don't I just get the Dirac mass term, and why they are still Majorana neutrinos? I don't understand completely, but I think Li Feng's book discuss this limiting case, how he recovered the Dirac neutrinos from this situation. But I will keep thinking about it. If I learn more about it, I will let you know. Okay, so let's take this equation. And as I said, this is left-handed. This is left-handed. And this is right-handed, right? So if we take the left-handed component of both sides, then I will get u dagger n L equal to mu 1 L, mu 2 L. Right? So,
may I ask a question?
sure.
So we don't在这个过程里头，好像看得出来，我们需要什么吸收的可能性。
不是，这个没有告诉你说 how big the neutrino masses are。吸收 mechanism 是要给你一个简单的办法，怎么样有一个 neutrino mass 很小。
有一个
啊，就是吸收 mechanism 给你一个简单的 mechanism， 可以让一个其中的 neutrino mass 非常小。这解释这个 neutrino mass 为什么很小的问题。等一下我就讲，这个接下来就讲，那你可以到时候你有问题再问，好吧？So if we have the equation, we can write down this n L equal to u u1 L u2 L, right? Then you just use the U matrix. There's cosine theta and so on, and then eta is plus minus 1. So we can put that in here. And you get mu L. Oh, here, this is equal to mu L mu C, right? So mu 1 L, mu L from here equal to cosine theta eta 1 square root cosine mu 1 L plus sine theta 2 mu 2 L. And then the right-hand charge conjugated field is minus sine theta square root eta 1 mu 1 L plus cosine theta eta 2 down. Okay? Okay. Now, we'd like to talk about seesaw mechanism. This is a simple way to small neutrino mass. Okay, so the input is followed. One, but I don't have a left-handed marijuana mass. Second, the MD, the Dirac mass term, is produced by the standard model takes mechanism. So this is what we discussed here. The other one is to have the MR, the right-handed marijuana mass, because the M equals this is much bigger than MP. So that's the input. So this is called stereo. Neutrino. Okay. So let's see what happens. Oh, it's all there. The mass aggregate is given by this. Okay, so let's take this. So we have M1, 1 and 2. ML equals 0, so we put M1 half MR minus plus 1 half square root MR squared, or 4 MD squared. And we assume that this mass is much bigger than this. So 1 half MR minus plus 1 half. We can do the Taylor series expansion of this. The first term is MR. The second term is 2 MT squared divided by M. Right? So the first one, so the M1 prime will be equal to taking this line, will be 1 half MR minus 1 half MR minus MD squared divided by MR. And then the leading term cancels, so this is equal to minus MD squared. And then this little MR called big MR. Right? And this will be equal to M1 times eta 1, and eta 1 is negative. So M1 equal to MD squared divided by MR. And I can write this as MD, and then a ratio MD over MR. And then because this is assumed to be much bigger than this, so this number is much less than MD. So this automatically gives you a very small neutrino mass, okay? And the other one, the M2 will be the plus sign, and the MR and MR add up, so ignore it. So this is what MR plus MR, and that's much bigger. So the seesaw mechanism was a way to produce a very small neutrino mass, and this was due to galvanic size. Maybe there's another person, I don't know. Okay? Any, do you have still a question? This. Okay? Okay. So this more or less finished the discussion of 3 ways to give neutrino masses. Then the next thing we can discuss neutrino masses. Okay. So if you have a neutrino mass, then what? The first thing is neutrino oscillation. Okay? So, suppose mu f is the Fourier eigenstate. And then mu I are the mass eigenstate. And so I can write neutrino of a Fourier f with some mixture of mass eigenstates mu I. So let me write as I v f I mu I. Okay? Now, as time goes on, you want to know what's the time evolution of this Fourier eigenstates. Then I write as I v f I, and then this is a mass eigenstate, so they will evolve according to the Schrödinger equation, and that is very simple because they are mass eigenstates. So A E I times T mu I. Okay? And the EI equal to momentum P squared plus a different mass on I squared. And it turns out the neutrino masses are very small. So we will assume that the momentum is much higher than this. So I can do the power series expansion. So P plus MI squared divided by 2P. Okay? Then this E minus IET will be equal to E minus IET. That's common to all mass eigenstates. And then I have this factor minus I and I squared divided by 2P. I can ignore this because when I take the absolute value square, when I compute the matrix elements, this is the overall phase sorting problem. So I can ignore this factor here and then write the mu f of t will equal sum over I V of I V minus I mi squared divided by 2p and then mu I. Now neutrino oscillation means that you change, the neutrinos change from one flavor to the other. So how do we express the mass eigenstates in terms of flavor eigenstates? So that's given there already, so I can do it again. So from that equation, from mu f equal to sum over I v f I mu I can get the inverse of this equation because this v is a unitary matrix. So mu I will be equal to sum over, let's call it f prime, and v f prime I is conjugate and mu f prime. Okay, so we can put this in there, and then mu f p equals sum over I, and then this f prime, and then I have this mu f prime here, and then I have this matrix elements, f prime I complex conjugate, and then I have the two factors, right? I have E minus I mi squared divided by 2p. And then the other factors have, what do I have? F R. Right. Okay? Now, I will need this combination later, so let me write this. Sum of I, V, upon I, complex conjugate, and then I have E minus I mi squared divided by 2p, and V f I. Okay, so this will be equal to sum over I, V f I, V minus I, mi squared divided by 2p, and I'm going to write this as a V Hermitian conjugate, and then I f I. Right? So this whole combination is equal to 3 E minus I m squared divided by 2p. If I treat this as element of a diagonal matrix with mi squared, and then I have a V diagonal, and then I have a f of 1. Right? Okay, so I need this later. So start from here. The general case is the same, but to be more explicit, let me just take a case of two neutrinos. Okay? And then the V, and furthermore, this are the, I only have the Dirac masses. I will tell you later what happened when you have Majorana masses, okay? Then this V equal to cosine theta, cosine phi, sine phi minus sine phi, cosine phi. Okay? And in the case of two units, let's say mu 1 is muon neutrino, mu 2 is electron neutrino, like this. And P, the probability for nu F going to nu F prime at time t is equal to this. This is equal to nu F prime nu F t squared. I give you this expression, right? So I take the scalar product of this with a nu F prime. And then you just pick up this coefficient square. So this would be equal to sum over I, VFI, VF prime I complex conjugate, and then of E minus I and I squared divided by 2P, P squared. Okay? So let's define delta to be this combination m2 squared minus m1 squared divided by 2p. Then the probability for the neutrino, muon neutrino to stay as a muon neutrino will equal to 1 minus 1/2 I squared phi, and then I get 1 minus cosine delta t. And probability for nu mu converted to a different one will equal to 1/2 sine squared phi 1 minus cosine delta t. Okay? And then the oscillation length. L is defined to be 4πp, and then I get m2 squared minus m1 squared. Okay? And then cosine delta t can be written as a cosine 2 pi r divided by L. And R is C times T. Well, here C is 1 in the natural unit. If I restore CT, that's the length, the distance. From neutrino sources, neutrino source. So you have some neutrino source here, and then somewhere here you will do a detector, and this length is R. Okay, and if delta is 2 pi r over L is much bigger than 1, very far away from. Then this oscillates very rapidly, and so essentially is 0. So in that case, P mu going to mu stays and mu will be equal to 1 minus 1/2 sine squared phi, and then P mu going to mu e will be equal to 1/2 sine squared phi. Okay? Now, because of this, that's why the neutrino oscillations can only give you information about the mass differences of the mass squares of the neutrinos and two square mass. You cannot get directly the information about masses. Today's lecture will be very short, so let me take 5 minutes.
Let me ask a question again.
Sure.
So, seesaw mechanism, I don't see the necessity
Yes.
for assume seesaw mechanism。就说seesaw的这个想法，好像并不见得一定需要。
那你
necessity。
Yeah, of course. You can always get a small mass by making parameter here.
用别的东西一样可以，对不对？因为你这里头要把 right-handed neutrino
变得很黑
对啊，right-handed 它又会变成 steroid neutrino。
对。
目的只是使这个质量变得很小，跟很大，对不对？
对。
我还看不出来，这个观念是不是一定有必要？
没有一定必要，但是是一个简单的办法，不 introduce new physics， 然后很容易让 neutrino mass 很小。
因为你假定它 right-handed 原来的 right-handed 的东西，对不对？变成另外的东西啊，它的质量一开始很大。
对呀。
是等于是assume 它有一个新的 steroid
neutrino 对，可是这个 neutrino 看不见嘛，因为 mass 很高，对不对？
我知道啊，我的意思说，这种想法，我在想这个想法是说，是有必要呢，还是没有必要
？Strictly speaking， 当然没有必要，因为你可以假定这个 Dirac mass term 那个 mass 很小，就 neutrino 的 mass 就很小，可是那就是不 natural。那有一个什么办法 ？Next best， 就是说，那一个 steroid neutrino 很 heavy， 那反正看不见，所以你 introduce 等于没有 introduce。但是这个的话就 imply， 另外那个 left-handed neutrino 就 mass 很小。这个是给我们的实验室，他们 paper 出来的时候，1978还是70几，30几年，我从来没看过，是现在因为要学这个东西才看的。Okay, let's get for 5 minutes break. So that's the first consequence of the neutrino masses, neutrino oscillations. I think so far the experimental data, as far as I understand, is that they see the change in the intensity of a particular beam. I don't think they actually saw the oscillation itself. So only see this appearance or disappearance. Okay, let's do the next one.
可以问一个问题吗？
Sure.
这个有关这个 neutrino 的一些，跟这个 K0 八不一样。
这个讲法不一样，对，因为这个完全是
不一样，因为 K0 八我们可以画出一些 box
对
的 diagram，
对
不对？
对。
所以你知道说它 in detail 它是怎么发生的，怎么发生mass 的difference，
对，
怎么发生 oscillation，
对。
但是neutrino的话，也应该有同样的东西，就是我写的那篇 paper。
我知道啊，但是是不是一定要那样就不知道了。
哦，但是要就是说你的 neutrino 之间应该有一个反应，然后有一个 operator， 有一个 field theory 的一个东西，让你知道说这个东西怎么发生。
这个也有啊，只是发生的办法不一样啊。
知道，你只是这个 overall 的，这是 overall 的描述，就是说你用这个，我并不是说这样不对，而是这样子，没有讲说你觉得为什么？
对，他没有告诉你这个 dynamical origin of neutrino masses. That's absolutely true. Actually, I should make a comment. We mentioned 3 different ways to give neutrino masses. The Dirac masses are produced by the ordinary Higgs mechanism, so that's fine. But the Majorana mass terms, where do they come from? I don't know. And nobody knows. All you can say is that they all come from beyond standard model interactions, okay? So that's your complaint, why neutrino oscillations are different from K0, K01. Okay, so let's talk about the second. Second consequences is called the neutrino mass. Double beta. That means in the nuclear reaction with beta decay, you don't see the neutrinos in the final state. And that can only draw you a Feynman, a quark diagram. So this is U quark, and this is D quark. And then emit the W, and then come out the electrons. And then there's a neutrino coming in this way. Okay? And then did I mention this? The Majorana mass, this is Majorana. Neutrinos. Majorana mass terms, you have nu L bar, nu L C. And you remember nu L C is equal to psi T something. Like I know something. Anyway. So they both involve this psi bar and nu bar here. So this violates this one violates electron number by 2 units. By 2 units. Okay? So if I have a Majorana mass term here, then the neutrino can come out this way. And this is a neutrino mass electron number violation. Then just here you can get another electron here. And then here's another W. And here you have another U quark. And here you have D. So you see that in the final state, you see 2 electrons due to weakened reaction, but you don't see neutrinos. So this is neutrinos less double beta decay. And this is the, I think, to show that neutrino is Majorana. I'd like to discuss another point. Is Majorana analysis. And neutrino oscillation. The question is just, let me say it that if you have Majorana neutrinos, then the neutrinos is equal to its antiparticle, right? So, the neutrino field phase is not arbitrary. The reason I mention this is that you go back to discussion about the mixing matrix for the quarks or the neutrinos with the Dirac masses. There's always a statement that because the quantum field's phase is arbitrary, you can absorb one phase. So if there are n fields, you can absorb n phases. But for neutrino field, Majorana mass, you cannot, this neutrino field cannot absorb a phase, because if you change the phase, then this condition will not be satisfied. Okay? So the question is this: can neutrino oscillations so because of this, so there are n minus 1 new phases in the mixing matrix. The reason is n minus 1 is because there's an overall phase which you can ignore, so there's only n minus 1. So if I write the mixing matrix, V, then the original mixing matrix U with the n minus 1 phases are absorbed. Then I have to put in another matrix here. P is a diagonal phase matrix. Is that clear? I have to put back this n minus 1 phases in here. Okay. So the question is this: can neutrino oscillations detect the phases P? And the answer is no. And it's very simple from what I have here. Okay, so I derived this. This is true for Dirac masses, Dirac masses or the Majorana masses. They all satisfy this condition. Then you see that if I put V equal to U times P, then this combination becomes V P minus I m squared divided by 2P V diagonal F1. And I put this in here. So U P V minus I m squared divided by 2P. And here is P diagonal U diagonal F1. Now this is diagonal, and so this P and that commute, and you see that the P E diagonal equal to 1. So this is equal to U E minus I M squared over 2P U diagonal y independent of P. So it's impossible to detect the phases due to the Majorana phases, okay, from neutrino oscillations. So the only way I know how to detect the Majorana neutrinos is through this neutrinos double beta decay, okay? And that's it. That's the end of my lectures. Okay? I would like to thank you all of you here staying through all 6 lectures, and really appreciate it. Thank you. Let me just say a few words that this series of lectures are memorial lectures in honor of Professor Crow. And when I was a student here in the late 1950s, when I entered Taida, I really didn't know anything about physics. All I learned was high school physics. It was very little. So I learned all the basic physics from here, and in particular Professor Crow. So I went to Harvard. I was able to keep up with the students there because of the training in Taida, and the major part is due to Professor Crow's teaching. So I'm always grateful to his teaching, and I always think of him when I do physics. Really. Thank you.
谢谢这个严东茂给了我们第一次比较 comprehensive 的 lecture， 前后原来是说有8个，后来变成6个，因为丢出 hurricane Sandy
可是我没有偷工减料。
我并没有，不是这个意思。就说我们其实我们应该想一想，Crow 这个人其实很特别，因为在40年代末期，台大建立起来，然后50年代、60年代，一直到70年代为止，对不对？就是说，在早期的时候，其实在真正懂得一个物理的人在台湾，那时候一开始都是用船来旅行，对不对？所以 Crow 其实很了不起的一个人，而且这个人应该对台湾的物理的历史很重要，因为可以说他有一阵子有20-30年，在这个我们的人开始有人回来的时候，像林清良等等，对不对？在那之前的话，其实 Crow 是可以讲说，对台湾的贡献其实很大。如果我们要讲这个台湾的物理方面的理论物理方面的历史的话，我觉得这个人应该好好的纪念。在现在的时代，因为现在资讯的时代，所以我们就不觉得这个很重要。但是如果没有 Crow， 那我们台湾其实会有一大片空白。所以以这个东西来讲，我希望大家 能够 enjoy 这次的 lecture。当然，我们有一个杰出的学长，对不对？就是说我们也希望以后也来继续办，因为我们觉得这种历史，物理的历史，还是要值得我们珍惜啊。我这次办这个东西，其实主要动机在于此。谢谢大家。还有什么谁要讲话的？我们欢迎。
好，谢谢。
谢谢，谢谢你。